Hello again. Today I will show you another example of the continuous system. Today I will show you how to find the governing equation of the vibration of rod. I mean, today we're speaking about the continuous system vibration, and it will be about the rod. I mean, it will be about such an element which has some longitudinal stiffness and which can vibrate only along its axis. Okay, I mean, we will be speaking about element which approximately looks like that. I mean, it will be some solid, some cuboid, let's say, with the area of the cross-section. It will be the parameter, because we're speaking about the element which has only the longitudinal stiffness, like I mentioned previously. There will be the Young modulus, because if we want to observe, if we want to find some vibration in the system, we need some restoring force due to the elastic properties. And of course, because the vibration is, let's say, some combination about the inertia and the restoring acting, we'll have to put some inertia parameter. I mean, in that case, it will be the rho, I mean, the density of our material. Okay. And here we have the hidden edge given by the dashed line, and the length of that thing, maybe I will use the green color, will be given by the L. And I will introduce some frame, coordinate frame. I mean, there will be the axis which denotes the position of the elements, like last time, and also I will introduce some function which will be function which describes the displacement of the particular points. I mean, it will be the function u at x. I mean, u of x t. I mean, that function describes the displacement of the displacement of every single point from our system. Okay? I mean, our function u of t, it will be such a function. Firstly, for better imagination of the problem, firstly I will take some slice of our beam, like last time. I mean, like in the case of the string vibration. Okay? I mean, we are dealing with such an element, really small element, I mean the infinitesimal element, which has thickness delta x, and also we have the position of that thing. I mean, it will be that distance. I mean, it's a x. Okay, I mean, we are speaking about the element which is distant from the origin of the value x, and thickness of that element will be delta x. If we are talking about the front view of that thing, it will look like that. Okay, and it's an initial time t0, let's say. Okay, it means that the position of that element, the position of, let's say, point 1 and let's say point 2 at initial time, it will be the x. I mean the general position of our element. I mean, here we have the x, let's say 0 in the initial position, and the position of the second point will be here, and it will be x plus delta x. Okay, and we introduced the function u of x, which describes the displacement of our element for every single point given by the x coordinate and for every single time. It means that function with unknown form u at x give us everything about the motion of our system. I mean, about the further position of our segment. Okay, and it means that during the evolution of the system dynamics, we have, let's say, some time not zero, I mean not initial time, some time t1, let's say, which is bigger than initial time. Let's say it will be, I will denote that it's a t0, here we have t1 bigger than t0 and it's not equal 0. I mean, it's not initial time. And after the deformation, after some time t, we'll have the new position of our segment. Because we are speaking about the longitudinal vibration, it will be displacement only along the axis x. Okay? And how to determine new position of the point 1 and point 2? If you want to find that distances, it will be given as the first position. It will be given as a displacement between the point 1, 0 and 1 prime, and it's given by the x u of xt, because here we have the position x and t, it's our time t1, let's say, I mean the general time. And if we are talking about that thing, I mean displacement from 2, 0 to 2 prime is given by exactly the same function, but it will be measured from the point 2, 0 to point 2, 1, because it's a Sachin function which gives us that information. I mean the information about the displacement of every single point, which will be indicated by the initial position of our element. It means that we have to take the same u, but at different spatial point. I mean, we'll have to take the value at the point x plus delta x and time t, because the situation is visible exactly at the same time t for the point 1 and point 2. Okay. And it is our introduced coordinate frame. Using that approach, we are able to determine important thing, okay? Because now we can consider the equilibrium of that point due to the Newton's second law. I mean, due to the second law, we have such a situation that acceleration of our segment, of mass of our segment, will be the mass of our segment times acceleration along the u-axis and x-axis in that case will be the net force which acts on the system. I will put that it's a sum of every single force which acts on our system. Fu, because it will be along the u direction of the x direction, because in our case it's exactly the same. Okay, and due to assumed coordinate frame, our u, it will be second partial derivative of u with respect to time. Second derivative, of course. How to compute the mass of the segment? It's easy, because it will be the volume of the segment. I mean dx times density times area of the cross section. We see that that part, maybe I will change the order. We see that thing, it's a volume of the segment, and if we multiply that thing, that term by the density, will get the mass of the segment, and it means that the net force will be given by du d square u over dt square. Okay, and now we have to deal with the sum of the forces which act on the system. Okay, let's consider the equilibrium of our point. Okay, I mean, let's again take the segment and let's consider what is happening with that element. Of course, we have the element with the thickness delta x, and the position of that thing is given by the coordinate x. I mean, that point 1, 0 is given by the x. That point, let's say 2, 0, is again given by the x plus delta x. Because we have the continuous system, like in the case of the function which describes displacement, we have the same type of the function which describes the stress. I mean, we don't know what is the exact form of that function, but we can assume that such a function exists and that function will be continuous, because everything in our system is a continuous function. Okay, I mean, on the left-hand side of our element, I mean, on the left side, we have the value given by the sigma of x and t, because the situation is given for the time t, and here we have the different value. Okay, because generally we cannot assume that that stress will be exactly on the right of the left hand side will be exactly the same on the right hand side. Why? Because also we have to take into account the influence of the inertia force. I mean, due to the inertia force, we will have some difference between those sides and those sides. I mean, those sides, because we need some unbalanced force. I mean, it will be for the coordinate x plus delta x of t, and now we will be able to compute the balance of the forces. Of course, I forgot about something. This time it will be delta x times area times rho, and now we have to compute the net force, and in that case we see that that force has the same phasing as assumed coordinate frame. I mean, here we see that the stress at the point x plus delta x of t times area give us the force from the right hand side. If we take exactly the same thing but at the point x and at the time t times a, we will get the force which acts on the left side of our segment. Okay, and it's a right hand side, and it will be balanced by the inertia force due to the Newton's second law. Okay, we see that we can take the common factor. I mean, it will be a times difference between values of our function, such a thing, and due to the conclusions from the analysis, I mean the part of the math, we can express, I mean we can estimate the difference of the function, especially if the delta x goes to 0, by the differential of the function. We know that generally differential of the function f, it's first derivative of the function times, let's say, differential of the independent argument. I mean, differential of the argument of the function. If we are speaking about the finite differences, we have to, or we can only propose some estimation. I mean, it won't be exactly equal to such a product. It will be something which will be similar to such product. I mean, there will be some computational error, but it will be small, and it will be smaller if that value will be small. I mean, for the smaller values, we will get the smaller error of the estimation of difference of the function values. I mean, here we have, in some approximation, here we have first derivative of the sigma with respect to x times delta x. And now we can simplify the problem by the a and the delta x, and we have as a final result, let's say final result because it's not the final step, we have the density times d square u over dt square equals d sigma over dx times nothing. I mean times 1 in that case. Okay, and now we see that we have a lot of variable in that problem because we have two independent variable, I mean the time and the spatial coordinate x, and also we have two unknown function, I mean the dependent variable, I mean the u and sigma. We have to find some relationship between the u and sigma. And from the strength of material, we know that the stress can be expressed as a product of the Young modulus. That is why we introduced that parameter at the beginning of our consideration, times strain. I mean, some kind of the indicator of the displacement in the system. I mean something which denotes or indicates the displacement or the deflection in our system. How to compute the strain? The strain can be approximated by the first derivative of the u with respect to x. It means that the sigma will be given by such a product. I mean the e times first derivative of the u over d x, and as a final result, now we have, if we put that formula here, we have such a simple equation. I mean, we have the rho times second derivative of u over t equals Young modulus times second derivative of u, I mean the same dependent variable, over dx square, and it will be such an equation as a final result. I mean d square u over dt square equals e over rho d square u over dx square, such a thing. And like last time, we will introduce some new variable. It will be, let's say, c square. I mean something which has physical meaning as velocity of the wave, which will be in our continuous system. Okay, I mean it will be such a thing. I mean, after the introducing that variable, we will get such an equation, which in many cases is called as a wave equation. And the methodology how to solve that problem, it's really, really easy. And next time, I will show you how we can deal with such simple problem, but it will be in the next video. Thank you for your attention. See you next time.